Guess who's back? Guess who's back? Yeah, now we've been looking at logic gates. So we continue. Remember to like and subscribe and tell us where you are in the comment section. Don't forget to do that, very important. Now we are looking at the last of the logic gates, which is the exclusive OR gate. If you missed some of our gate sessions, just look up some of our older videos and you will see we have done everything from the buffer to the NOT gate, the OR gate, the NOR gate, the AND gate, the NAND gate. We've done all those gates. We've even done the exclusive OR gate. Today we do the final one, which is the exclusive NOR. Alright, let's bring up our software. There on the taskbar we hit the software. Remember, it's WPL from Delta. For the DVP is the DVP-PS02, and well, I clicked there. I thought this would be gone. This is from our previous session. This is the exclusive OR gate. Now I would like to start a new one. Remember, I will start a new one, Control N or that icon, or this time I will go and hit down on the File tab and click New Project, and then this is yes, we want to start a new project. Now obviously we start with naming the project is still logic gates, so I want to give that as a title, logic gates. Alright, and then our the PLC we're using is the SS2, so we go there and you say SS2, we come there, we name our, which is the exclusive, let me rather say Delta WPLSoft. Did I say soft? And then exclusive OR gate. No, exclusive NOR gate, which means it's the opposite of the exclusive OR. Again, I will use Boolean algebra for this because it's much quicker and easier to explain it using that. So let's get our platform, programming platform, our letter diagram mode there. Let's expand it. Let's make it huge, and then there we are. Now we can start and say what do we want. We want to, let's start with the Boolean algebra to assist. We know that our exclusive OR gate is, let's take the pen, y is equal to, let's say, a, b, this is an AND gate with the inputs inverted, not, or a, b, as is. So this is what? This is an normally closed for the A, normally closed for the B in series, and then it's gonna be in parallel with a set that is normally opens for the what? For the AB. This is as easy as it gets. So let's go and put this on the. So what do we want? We want an AND gate for these two. So AND gate, we know now it is there. Oh, I need the select. Now this is the x0, one of the inputs. Now remember, a it is the same variable, b same variable. So I've got two variables here, a and b. So my other variable is remember, AND gate means series. So all I'm going to do is two different variables, a and b are in series, the AND gate. So there is our two variables, but they are both what? They are not, I made a mistake there. This should be LDI, alright, which means they're normally closed. That is also LDI, which means normally closed. So LDI, so it's easy to change it over, so no train smash. So there is our AND gate, our series of the normally closed. Now one O is a what? O is a parallel network, and then now we want an AND for the A and the B, so which is two normally opens. Normally open 1, that would be the same variables. A is x0, so it's again x0. That's fine, but this time around we're not going to cross it, so it's going to be the normally open because there's no line on top. And then the B is x1, so x1, we're just going to say load another one there, but it's x1 again. There's no cap, so it's normally what? It's normally open. So if I do this now, all I do is say that must drive me my output. So I will say out, and I will use y0 as my output. So what it means here is, if I use that reasoning there, this will be, alright, this is the general scenario. Now for this specific case, I would have my output is y0 being equal to A is the equivalent of x0, the one input, and then B, what am I saying? B is the equivalent of x1, the other input, okay? But both are not, or which is the parallel. Then it's A is x0 with B, which is x1. So this is basically, this is the general scenario where we're using A's and B's, but for this specific software, it's X's for the for the inputs and Y's for the outputs. So yeah, I guess that is so straightforward. Only thing we have left is to test whether our circuit works. Let's see whether our program works fine. What we're going to do now is we're going to go, you know, by now we're supposed to go to the simulator. Let's debug and see if we have any issues. When we debug, all of them are identified. The normally opens, the normally closed. You can see that the normally closed are already green, meaning that they are ready to fire. Now let's get out of debug mode, and then we go and say let's load it online. Let's put it online, and then now it's on stop mode. Obviously we have to then run it, and then once we say run, confirm it. As you can see, instantly we've got power. Let's check our pen again. So this is us having two inputs, x0 and x1. This is our table, our truth table. So when they are both, I didn't activate anything, they're all set to off. We can prove that by coming there and saying, are you off or on? Let's set it off, because we didn't do anything, so it's, by default it's off. So set off, you can see nothing changes. You expect the same here. Nothing changes. It's set to off. Alright, so now when they're both off, you can see our output y0 is high. So we take our pen and say y0 is high. So high is 1. Alright, so now when you come and you look at the what? At the next combination, which will be 0, 1, meaning that I go to x1 and I set it on. So I go to x1 and I say I set it on. Set on. You can see immediately the normally closed. Once we activate what's normally closed, it breaks, and what's normally open, because this is the same variable, what's normally open here closed. So if you activate x1, the part that is normally open will close, the part that is normally closed will open. So what you see here is that there's no continuity here, there's a break here. This was already open, we didn't set this on, so this is open, so there's no way power will go through. As you can see, our output there is actually off. So what we do, we come and you say that combination gives us off here. Alright, it should be obvious to see our next combination is going to give us the same result, but let's prove it. Let's go ahead and say, okay, we set you off, we set you on, let's set you back off. So what we do is we right click on that, set off, and you can see the normally open goes back to its state. Now what we're going to do is we're going to activate x0. So on the x0 now we say we set on. As you can see, it is the same thing. So what's normally closed therefore breaks after activation. What's normally open is then closed when you activate that contact. Alright, so now you can see again That results in a break there. That resulted, this already is by default broken, so there is no pathway for the power. Therefore, as you can see, again, this is not greened out, so this is off. So what does it mean? It means that we have no output here. Okay, so now we have the last situation, which is, how about if you set both of them on? All right, right now we've set the first one on. We've set the first one on. Let's just set the second one. Let's just remind you that we set it on. Set on, so nothing will change. But if you set this one on, now you see that yes, those were both normally closed. So once activated, they open, and these ones were normally open. Once activated, they close. So you can see now you have a pathway that will supply our load. Therefore, our circuit is closed, and we get power. All right. So now you can see this is equal states 0, 0, 1, 1. So this is why this is also called the equality comparator. When the two are comparatively equal, the gate gets happy. So you can see when the two states were equal, when the two inputs, when the two contacts were at the same state, at an equal state, you find your what? You find your equality comparator or the exclusive no being happy. What we forgot to mention in the previous session with the inequality comparator, with the, remember that for the exclusive or this is the exclusive no that we just did now. What we forget to mention with the exclusive or, remember the exclusive or is the opposite of this. So when you had x0 and x1, when the two were equal, your y0 was the opposite, which was a 0. When the two were not equal, if you remember correctly, here is zeros, that one it was ones with the equality, with the exclusive or, and then when it was an end state, he said though exclusively or, and that was the output. Now if you look, when the two inputs were unequal, okay, your gate was happy, your gate gave you high outputs when the two inputs were unequal. So this is also called, the exclusive or is also called the inequality comparator. Okay, so that is another name. We forgot to mention this in the other video, comparator, but then anyway, there it is, you catch up. So these are our gates. I hope this was fun, because this was the last of our gates. Remember to like, because I believe that it was very likable. And also please send us your comments and tell us who and where you are. That will make us very happy. You don't have to tell us where you are, you just have to tell us don't have to tell us who you are, but it will be nice to tell us where you are, so that we can at least know how far we are reaching. All right, now till we meet again for the gates, we are still doing PLCs. We're not done with the PLCs, but as for the gates, I rest it right here. The next thing that I'll look at will be the further programming. Or let me just call, we're going further with the programming. So stay tuned. Let's meet in the next session. Ciao. It takes a little bit, it's a little bit of a